Hi you guys, today I'm going to talk to you about single displacement reactions as well as double displacement reactions. Okay? So what you will need are your notes as well as your reference chart with the activity series on it as well as your solubility chart. Okay? Alright, let's get started. So first of all, single displacement reactions is the same thing if I say single replacement reactions. Okay, it is the exact same thing. It doesn't make a difference which word you use. The idea is that you are actually replacing one of the elements with another element in the compound here. So you end up getting a new compound that has been replaced by an individual element. Okay, so you've got here a compound. Keep in mind that the first element in the compound is always your metal. It has a positive charge, okay? It is the cation. Your second element that you have in your compound has a negative charge. It is the nonmetal, and it is the anion. So this is the ionic bond, okay? It is an ionic bond. Because you have the metal or the cation first and the nonmetal or the anion that is second. The second element that you have can be either a positively charged cation or it can be negatively charged or your anion, okay? And depending on what this element is, whether it's a metal or a nonmetal, will determine what product you're going to have in your reactant. Okay? So if I have this compound and my second element happens to be a metal, then this metal is going to be in competition with the metal in the compound. And that's always the first element. If this element right here, the second element, happens to be, or the singleton metal happens to be more reactive than the metal in the compound, then your reaction is going to take place. And this element will then replace this metal, and it will bond to your nonmetal, which is right here. So, of course, you're going to write your metal that is written first, and then your nonmetal second. And then this element right here, the one that used to be a part of the compound, will be left all by itself as a singleton. Okay? Yeah, the same thing happening if this element happens to be your nonmetal. If it happens to be the nonmetal, then this element right here will be in competition with the metal in the compound, and it will then react with the metal in the compound. So again, you would write your metal first and then your nonmetal, and you would have your anion that once was a part of your compound originally will be by itself, the singleton. Okay? So that is a reaction. It's a single replacement because one element is being replaced on here. Okay? So in order to determine whether this reaction is going to take place, depending on the C, whether it's a strong reactive enough metal or a reactive enough nonmetal, you need to look at your activity series chart. So on top of your activity series chart, go ahead and write single replacement reactions, because that is what we're really going to be using this for. We're going to be using this for only single replacement reactions. Okay, so the way that you actually use this is that you have the metals on one side and you have your nonmetals on the other side. So this is your metals, which means that they are positively charged, and these are your cations. Your nonmetals or your halogens are always in the second column or the second part of your chart, and these are, keep in mind, negatively charged, and these are your anions. Okay, it doesn't say this, but these are your nonmetals that show up on your periodic table, your halogens. So if you look at this chart right here, you've got your less reactive elements that are at the bottom and your most reactive elements that are at the top. So as you move up the chart, your elements will become more reactive. So lithium is the most reactive element, where you have gold that is the least reactive of the elements. That means if lithium was in the reaction, it will always go through. If gold is in the reaction, chances are your reaction is not going to go through and you're going to have a no reaction. So let's go ahead and try these problems, okay? So right here you've got the most reactive metals replaces the less reactive metal. So you've got, I'm going to bring it closer, you've got potassium, so go ahead and write potassium, is added to a solution of silver nitrate, and that would be AgNO3. You're looking at the states of matter on your periodic table. Potassium is black, therefore it's a solid. Using your solubility chart, you've got sodium nitrate, which is aqueous. Okay? And then we draw our arrow, and we've got in here, is this reaction going to take place? If you don't understand how we got this to be aqueous, hold on for a minute, because I will talk about it when I get to double displacement reaction, how I determined it using the solubility chart. So just hold on for a little bit, okay? So the two elements that we are actually comparing in this case are the two metals that you have. Because potassium is positively charged, I am going to be comparing it to the silver on the chart and seeing which is more reactive. So if you are looking at your chart right here, okay, I've got my potassium, which is right here, and then if I keep going, I've got my silver. Barely, you can barely see it. It is right here at the bottom. So let me see if I can do that. Okay. So potassium's up here, and then silver is all the way down here. That means that potassium's higher. It is more reactive than the silver that you have. So you are going to then go back to your sheet, and you're going to say this reaction will take place. This potassium will then react with the nitrate here, and when it does, your new reaction will be potassium nitrate plus silver. Okay, on your periodic table, silver is black, so it is a solid, and for right now this is aqueous, and I'll show you later on why it is aqueous. Okay, and we are balanced in this case, one potassium, silver, one nitrate, one. So we are balanced. We do not need to balance. Okay, so that's how this reaction is going to take place. I'll do one more reaction, and then you can do zinc on your own and check with me. Okay, so the next one is in this case sodium is added to water. So I'm going to write sodium is added to water. Now for this reaction, all of the elements in here, you are going to use water instead of using H2O. You're going to write HOH. And the reason being is because you really want to see that hydroxide group in water and how it reacts. And this H right here happens to be the metal. Your hydroxide group happens to have a negative charge. So the state of matter for water is always liquid, and your state of matter for sodium, it happens to be a solid. Okay, so you're going to, sodium also has a positive charge. So the two elements that you are actually comparing on your chart are sodium and hydrogen. So looking at your chart, going back to your reactivity right here, if you're looking at sodium and hydrogen, which is right here, sodium is right here, hydrogen's right here, sodium's higher in the chart. It is more active than or reactive than the hydrogen. Thus, this reaction will take place. This sodium will then react with the OH, okay, with the hydroxide group. And when that happens, you are going to get hydrogen plus sodium hydroxide. Remember, sodium hydroxide is a base, and all your bases are always aqueous. Just like your acids, all your acids are always aqueous. Okay, so keep in mind that if you have acids, Okay, they will be in the they will have the state of matter of aqueous, and the way you can tell it's an acid is that the H is written first, and then you have X, element X. The element X is always your anion that has a negative charge. It's the nonmetal. Your base, on the other hand, will also be aqueous, meaning it is mixed in water, and it'll have X, which is your metal or your cation that has the positive charge, and then OH will be attached to it. So whenever your OH is your anion, which is what it is in this case, it is a base, and we would say it is aqueous. Don't forget and write it on here, Hofbrinkel. Okay, so hydrogen, it's part of Hofbrinkel, so it's H2. And yes, this is your gas because all of the Hofbrinkels except for bromine, which is a liquid, and iodine, which is a solid. But this hydrogen is a gas at room temperature. So this reaction will take place. Sometimes you'll have an element, such as an element over here, that is higher up on that is lower on the chart than the element that is attached to the compound. In that case, it is okay to write no reaction, because truly a reaction would not take place then. Okay, so that is possible. But we're going to do our best, and we're going to complete this reaction. So when you balance it, you get two sodiums, and then you have now 4 hydrogens. So we're going to put a 2 over there and make it 4 hydrogens and 2 oxygens. Okay, so go ahead and do the third one on your own, and look up to check your answers. But if you're having trouble, then just listen on. And you don't have to fast forward. So zinc pellets are added to hydrochloric acid. Zinc is a solid in the periodic table. Hydrochloric acid, remember it's got the hydrogen in front, so we're going to say that the state of matter is aqueous. Okay, that means we took the acid powder, or the acid, hydrochloric acid, which was in powder form, and we mixed it in water to make it. Okay, and we want to compare zinc that has a positive charge to hydrogen that has the positive charge on there. So we're going to go back to our activity series chart, and we've got zinc that is right here, and then hydrogen, which is right here. So zinc is higher than hydrogen, so this reaction will take place. This zinc will then kick the hydrogen out, and it will bond to the chloride in here. So I'm going to turn it around, and I'm going to write zinc chloride. Keep in mind that zinc has a 2+ charge, so if I write this really small, it's got a 2+ charge. Chlorine has a 1- charge. Then if we write this, we would have 2 written right here for our reaction. And then of course you've got, that wonderful diatomic hydrogen gas. Don't forget, it's a part of Hofbrinkel. And then of course this is in the state aqueous. Okay. We're going to balance this. So in order to balance it, you have 1 zinc, 1 hydrogen, 2 hydrogens, and 2 chlorines. So if we put a 2 here, that should give us 2 hydrogens and 2 chlorines to balance everything out. So the next one is, we're talking about the halogens, so we will be looking on the other side of the activity series chart. So go ahead and write your equation right here. You have fluorine gas that is bubbled through a solution of silver bromide. So you have AgBr. AgBr is it is a solid, I believe. Okay, so we're going to write a solid right here. And is this reaction going to take place? That's the question. Keep in mind that we are looking at, now in this case, fluorine has a -1 charge. Okay, so keep in mind that we're looking at the charges for it. So fluorine has a -1 charge, and I'll write that here. Just like for zinc, I will write that it has a 2+ charge. That's what you're always comparing. You're always comparing those charges. So you've got fluorine here, and you've got bromine, which also has a negative charge. So you're comparing these 2 elements to one another. So the question is, which one is more reactive or higher up on our activity series chart? It is fluorine that is more reactive than bromine. Since fluorine's higher up, it's more reactive. So this reaction will take place. Your silver is then going to bond to the fluorine and not to the bromine. So in this case, we're going to write bromine. Don't forget, it is a Hofbrinkel. So we're going to write Br2, and it's a liquid. It's blue color on our periodic table. And then our new reaction is silver fluoride. Keep in mind, silver is plus. It's a metal, so it's going to be written first, and then fluorine. And this is a solid at room temperature. So we're going to write this reaction right here. You guys, it really does not make a difference if I write the compound first and then my individual element. I changed over here and I wrote my individual element and then my compound. It does not make a difference. Okay? Now I'm going to complete this equation by balancing it. So I've got 2 fluorines, 1 fluorine, and I've got 1 silver, but 2 bromines and 1 bromine. So if I put a 2 here, that'll give me 2 silvers, right? So if I put a 2 here, and that'll give me 2 fluorines and 2 fluorines. I've got 2 bromines and 2 bromines. So I am balanced. The last one that I have here for a single displacement is bromine, which is diatomic. It's a liquid, is added to ammonium iodide. Okay? And it is aqueous. Okay? And is it going to react? Well, we're looking at this reaction. We are, guys, looking at bromine, the charge of it, it's a -1, and iodine has a -1 charge. So which one is stronger? Which one's more reactive and will cause the reaction to go through? And so we are looking at bromine and iodine. They're right next to each other, but nevertheless, the bromine's higher up and then iodine. So the reaction will go through. This ammonium will bond to the bromine and not the iodine. So the reaction will go through, and I'll write it the other way. So you'll have ammonium bromide right here, ammonium bromide, and this is an aqueous solution. Okay, plus you have your iodine. Iodine is part of Hofbrinkel. Hofbrinkel, don't forget. And because it is part of that, it is a solid, or it is black on the periodic table. So it is going to be your iodide, your black, your solid here. We'll complete this reaction by balancing it. So it is going to be, the coefficients are going to be 1, 2, 2, and then 1. So we've got 2 bromines, thanks to this 2, 2 ammoniums, 2 iodide, because remember, you distribute this 2 for each of the ions here, and then you've got 2 iodides right here. Okay, so this is our single displacement reaction. Let's talk about double displacement real quick. Double displacement is now you are replacing 2 of the reactions. So you always have the metal written first and then your nonmetal, metal written first and your nonmetal. And this reaction will go through, and when it does, you will have now this metal will now react to this nonmetal, and this metal will react to this nonmetal. And when that happens, you've got new compounds where you have your metal is bonded to a new nonmetal, and then you have your other compound, you have your metal and your nonmetal written, or your cation and then your anion written. So this reaction occurs whenever you have 2 ionic compounds that are dissolved in an aqueous solution. It's essentially, you guys, the exchange of ions. That's what's happening. In order to determine what state of matter or descriptors are going to be formed, you need to be looking at your reference chart. So it's not blue, rather it is pink on here. So you have the pink one, and the way that you look at this chart, it is your solubility of some ionic compounds in water chart. And so, make it small. There you go. So this is your chart. You have your negative ions right here. Your negative ions, of course, they have that negative charge. They are your nonmetals, or we call them your anions. Okay? And your positives are the second column. So we're going to write a plus. And these are, of course, your metals or your cations. And they tell you which compound is going to be formed. If your compound is soluble, that means it is aqueous. It's mixed in with water. If it is not soluble, that means that it is the precipitate that is formed, and we initial it PPT, or we can also say that it is the solid that forms in the liquid, and we can put a lowercase s as the symbol, as a descriptor for it. And I'll show you how to use this in a minute. So throughout our single displacement reactions, I talked about how it was aqueous, or it was a solid. And I'll show you how to do that now with your double displacement reactions. Okay? So when we are looking at this, whenever you have two solubles, compounds that are mixed together, one of the compounds will be insoluble. When I say it's insoluble, I'm saying that it's a solid that's going to form. Okay? And it's going to be a very cloudy substance. A lot of the times we say that it is a precipitate, or I initialed it on your chart as PPT. Okay? So on your reference chart, this is the precipitate that's mixed in with your aqueous solution. Okay? So let me give you an example of it. The first type of double displacement reaction that we have is called a precipitation reaction. So we have lead to acetate. And I should not write that on there for you right now. Oh, we'll go ahead and write aqueous, okay? Reacts with ammonium. Reacts with ammonium phosphate. So you go ahead and write that. Lead to acetate reacts with ammonium phosphate. And what are the products going to be, and what is the state of matter of those products going to be? Well, first of all, go ahead and we're going to go ahead and write our product. Keep in mind that this is positive, this is negative, positive, negative. How did I get this equation? If you're still having trouble writing equations, keep in mind I said that this is lead 2, so this is 2 plus. Acetate is 1 minus. It's an ionic compound, so it's stable, it's equal to 0. So exactly what are my number of atoms going to be? This is going to be 1 lead, and then I'm going to have 2 acetate ions that are going to be added. Okay? For this one, keep in mind that this is 1 plus ammonium, and then our phosphate is 3 minus, is equal to 0. And what are how many atoms of each am I going to have? To make this equal to 0, I'm going to have 3 over here and 1 over here. So I'm going to need 3 ions of my ammonia. I'll write this 2, 2. Okay, so that's how I'm getting my equation that I have here. So in this case, I've got this lead that's going to go ahead and bond to my acetate, and I'm going to have this ammonium that is going to bond to my, I'm going to have my lead that's going to bond to my phosphate, and my ammonium that's going to bond to my acetate right here. Okay, so my new equation, it doesn't matter which order I write it in. I can write it in any order. I'll just go from this place, but if you want to write the ammonium first, that's fine too. But keep in mind that it is lead 2, so you're going to keep the same charge for lead throughout this equation. So it's going to be lead, Pb3, and then phosphate with 2 ions of it. And then, of course, we're going to write ammonia. Okay? In our reaction. Now, we want to find out the state of matter for each of these. Since this is a precipitate reaction, let's see. We have lead acetate. So go back to your chart right here. I'm going to make it small. Okay? So you can see it. So my anion in this case is acetate. So I'm going to find acetate in here. Acetate is right here. And I'm going to go right across. This is my anion. And I'm gonna match it up with my positive, with my cation. And my cation in this equation is a lead. So if I go straight across, and I can only go straight across, it says any positive ion except for silver and mercurius. Is lead one of the exceptions? It's not silver, nor is it mercurius, so therefore it is soluble. So that's why I have aqueous there. I have ammonium phosphate. If I have ammonium phosphate, I'm going to find ammonium. I'm going to find my phosphate. And if you look in this chart here, my phosphate's down here, and it's connected to, is it bonded to anything in the alkali ions? Keep in mind, alkali ions are group 1 of the periodic table, just like alkaline earth metals are group 2 of the periodic table. But alkaline ions are ammonium. Well, this phosphate is bonded to an ammonium. So because it is, then it is soluble, meaning it's also aqueous. Okay? Then to see which one of these is going to be the solid or the precipitate that is produced, I'm going to look up again phosphate in here, and I'm going to see phosphate is bonded to, my phosphate is bonded to lead here. So phosphate, alkaline ions or ammonium, no. Lead is neither one of those, so I'm going to go to the second choice, and it says any other positive ion. That would be not soluble, which means that that is the precipitate or the solid. So this will be the solid right here, or the precipitate that comes out. Ammonium acetate, on the other hand, if I go ahead and find acetate, any positive ion except silver or mercurius. Well, that's not ammonium. Ammonium's neither one. Therefore, it will be soluble. Okay? If acetate happened to be bonded to that, then it would not be this, and it would be a solid or not soluble. But in our case, our acetate's bonded to ammonium, which is neither one of these. So this is true. It's going to be soluble. So it's going to be aqueous. Okay? What this means is that if you have your test tube, and in your test tube you're going to have a bunch of liquid, and then you're going to have some solid at the end. Well, this solid happens to be my lead phosphate, and the liquid in here happens to be my ammonium acetate. That's what this is saying. So the next reaction that we have is acid-base neutralization, and you want to highlight this in the reaction in your notes, where if you have an acid and base, it will always form a salt and water. That is your typical reaction. So my acid and base that I'm giving to you is sulfuric acid. So go ahead and write the equation for that. Remember sulfuric acid, so it's always going to be aqueous. It's an acid. And my base will be sodium hydroxide. It is a base, so it's always going to be aqueous also. And what is it going to produce? Well, you're looking at the positive and the negative. So this hydrogen will bond with the OH in sodium hydroxide, and this sodium will bond to the sulfate. So our new equation that we have will be sodium sulfate plus HOH. Okay, and I want you to write water as HOH. It does not make a difference if you write HOH first and then sodium sulfate second. It doesn't make a difference. Well, we already know what the state of matter for this water is. It's liquid. Okay, but this right here, sodium sulfate, we're going to look it up in our solubility chart right here. Our anion in this case is sulfate. So we're going to find sulfate right here, go across, and our sulfate is actually bonded to sodium. So it's not calcium, strontium, barium, radium, silver, or plumbus. So we're going to ignore this, but there's a second option. Yes, our sulfate is bonded to any other positive ion, so that makes it soluble. So in this case, it is aqueous. Okay? So if you look at this reaction, this is the acid, this is the base that is producing the salt and the water. Okay? So this reaction is actually coming true. So whenever you have an acid-base neutralization reaction, your products are always going to be the salt in water that is produced. Okay? We have one more double displacement reaction. And I would say that this is the one that students often miss because it is deceiving. So you want to put a star next to it. Okay. So, and you want to highlight this, that it always produces an acid plus a metallic carbonate will produce a salt, water, and carbon dioxide. Of course, this metallic carbonate could also be your bicarbonate. It could be a metallic bicarbonate. Either one, as long as a carbonate is present, this reaction, when reacting with an acid, will occur. Okay, so what really happens is you get an acid that is bonded to a metallic carbonate. And in reality, what happens is that it ends up producing a salt plus carbonic acid. Okay? And it is this carbonic acid, when you break it down, eventually you will see it. It will form your water plus carbon dioxide. And the gas that it is produced is gas-forming reaction. So, let me enlarge it again. So in this case, it is gas-forming reaction. Well, the gas that it is producing is actually this carbon dioxide. So the tricky part of this is that when this carbon dioxide forms, if it's not in a closed container, you will miss this reaction entirely. So this reaction actually needs to happen in a closed container in order for carbon dioxide to be found. Okay, so my reaction is hydrochloric acid reacts to calcium carbonate and to produce calcium chloride and carbonic acid. It's the same concept as before, where the cations and the anions are exchanging one another. This carbonic acid will then break up and produce water plus carbon dioxide. In a closed container, you can see this water and carbon dioxide being produced. Okay, water, of course, is a liquid. Your carbon dioxide is a gas that is being produced. That is the gas that is being produced in this reaction whenever you have an acid and a metallic carbonate. Sometimes this metallic carbonate can be a bicarbonate that is being used to produce this reaction. And of course, when you use your solubility chart, keep in mind that this is aqueous. This is an acid, so it is aqueous also. Okay? So when you write this reaction, either you can write it this way and then go ahead and balance it, or you can have this reaction and then just write write your salt, water, carbon dioxide. So we would have hydrochloric acid plus calcium carbonate, and this is aqueous and produces calcium chloride, which is aqueous, plus you have your HOH, which is liquid, plus your carbon dioxide, which is your gas. So either way is acceptable. We can write it like this, or we can write it like this. Just depends on what I'm asking, which one's the acid or where's the gas in this reaction. Okay, so this is my lecture on single displacement and double displacement, and hope this answers a lot of your questions. Bye, guys.